Then I'm going to do a small circle of radius delta. And I'm using this formula here for delta. So step 2, if I can show that v dot is less than or equal to 0, and v dot of 0 is equal to 0, i.e. I'm showing v dot is negative semi-definite, then v cannot increase. And each value, each constant value of v is a level set. In our case, an ellipse called a Lyapunov surface. So this ellipse I've drawn in here is a level set of v. In other words, v has the same value everywhere on this ellipse. In fact, v is actually equal to d on this ellipse, right? So if I use a bigger number, so this might be like, this might be like v equals 2, right? But if I had a bigger number for v, my ellipse would actually be bigger. So if I had something like this, that might be like v equals 3. Whereas if I had like a smaller value, this might be like v equals 1. And v is kind of like the height. So you usually think of this as a bowl. So we're like looking down into a bowl shape, basically. So this is actually at a greater height. So if you like, we're in the Saddle Dome. This is like a row of seats in the Saddle Dome. That's a little higher than this row of seats. That's a little higher than this row of seats. Okay.
So if there was a large disturbance that knocked the value of x, one of the x's, for example, outside of that circle, does that mean the system becomes unstable then?
Well, okay, so
Or it just means you can't prove it's still stable?
it all depends where this happens, right? So v dot being less than 0, it all depends where this is true. So as long as I'm in an area where v dot is less than or equal to 0, then it can't go unstable. But if your disturbance that you just described knocks me out of a region where I can guarantee that v dot is less than or equal to 0, then it may indeed go to infinity, right? So it all depends where on this diagram that v dot is less than or equal to 0. So we have to kind of, it's not apparent from that diagram. The diagram just has information on v, it doesn't have any information on v dot. So v dot is something we have to go and calculate.
Okay.
Not something we can see in the drawing itself. So set delta equal to the square root of d over p max. Okay? So if I do that, so if I start in here, basically I'm talking about v dot being less than or equal to 0. So I can't go up in height. So remember, I'm thinking of this as like the saddle dome. So if I go this way, I'm also thinking of going up. So because v dot is less than or equal to 0, I can't go up. And in that diagram, that also implies I can't go this way, because I'd be going like up rows in the saddle dome, right? So I can't go uphill, because I've kind of, somewhere else I've kind of proven that v dot is less than or equal to 0. So that means I can only go downhill. So I can only go down seats in the saddle dome. I don't know if that's obviously something like, oh, it's going down. Let's see. Let me draw this better. Maybe something like that. Okay? So I can't go uphill. I'm kind of constrained in here. So you can see that I can't go beyond this radius epsilon. So I have in fact found a delta such that if I start within delta, I'll remain within your ball of radius epsilon. Because the very worst case scenario is where I'd be like going like this right along the edge. But there's no way I can actually get outside of epsilon as long as v dot is less than or equal to 0. Because I can't go uphill. I can't go up these rows in the cell. Right? So since v dot is less than or equal to 0, v of x cannot increase. So a trajectory that starts in my circle of radius delta stays within the ellipse, which we're also calling the Lyapunov surface, and thus also stays within your circle of radius epsilon. So let's just kind of summarize this. So summary, you give me epsilon to, I use some v of x equals x transpose px with a positive definite symmetric matrix P, and then I calculate d equals epsilon squared P min to ensure d equals x transpose px is an ellipse within circle radius epsilon or I calculate delta equals square root of d over p max, which is the inner circle of the ellipse, if you like. That's one way to call it anyway. So then the last thing would be is that I verify that v dot is less than or equal to 0 within this circle of radius epsilon. Then, if the trajectory starts in a ball of radius delta, it stays in x of t is less than epsilon. So you can see how now you can, I haven't done a formal proof of the theorem, but now you can see how the theorem and the definition match up, right? How the theorem allows you to calculate a delta based on an epsilon, essentially. So I did talk about calculating d here, but I didn't talk about calculating p. So any ellipse that fits within that circle is fine. So there's no like one correct answer for p. There's lots of different ellipses that can fit inside the circle. But we will look at a way to calculate p. So I will show you how to do that. But it's not like the only way to calculate p, because you can imagine any ellipse that fits within the circle is fine. There's an infinite number of ellipses you can fit inside the circle. But we'll look at one way to calculate a nice ellipse to do it. So any questions about that? How the stability definition and the theorem all fit together? So that kind of makes sense.
So the initial state has to be inside the small delta in order to stay within epsilon, the smaller delta. So
I wouldn't say it has to start within delta.
Oh, okay.
I wouldn't put it that way.
Oh, okay.
But I would say I found some initial conditions that work.
Oh,
There
okay.
may be other initial conditions that work as well.
Mm-hmm.
But I have found a set of initial conditions within this ball of delta that will kind of guarantee me staying within this ball of epsilon. But there probably are other initial conditions as well that will work.
So does that mean you want delta to be as large as possible then, if you want to have the widest possible set of stable initial conditions?
That's probably not necessary. Theoretically, you might be right, but that would be complete overkill.
Oh, okay.
It's completely unnecessary, for sure. You don't have to do anything like that. So basically now I'm going to talk about calculating that ellipse P, finding the equation for this ellipse. And strangely enough, I'm going to have to go back to linear systems to show you how to do it. So let's look at linear systems. So we're going to forget about nonlinear systems for just a bit here. If x dot equals f of x is linear, then I can always write it as x dot equals ax, where a is a matrix, and x equals 0 is a globally, exponentially stable equilibrium point if and only if all eigenvalues of A have negative real parts, i.e. A is negative definite. That's another way of writing that in terms we've seen in this lecture. So consider function b equals x transpose px, where p is symmetric, positive definite. Then b dot is equal to x dot transpose px plus x transpose p dot x plus x transpose px dot equals x transpose a transpose px plus x transpose pax. Yeah, I've heard it say p dot is 0. This is a constant matrix. Equals negative x transpose qx. Oops, just skip the line here. Sorry. X transpose bracket a transpose p plus pax equals negative x transpose qx, and negative q equals a transpose p plus pa is called the Lyapunov equation. So normally what one does here is you choose a symmetric, positive definite Q to calculate P from the Lyapunov equation. So again, this is kind of one of these things where I challenge you to, there's a difference in thinking between grads and undergrads. So undergrad would probably see a mathematical equation like that and say, well, solving for P is going to be ridiculously hard when they ask me to do it on the final exam. But a graduate student just says, oh, that's probably like one line of MATLAB code, I'll just type it in. So that's what we do here, we just like use MATLAB to solve it. So for us, it's like easy, okay? So calculate P from the Lyapunov equation. So in MATLAB, we have to do P equals Lyap A transpose Q. So unfortunately, the MATLAB engineers who were writing the code had some access to some weird, strange textbook that wrote this Lyapunov equation the other way around. I don't know what the textbook is because I've never seen anyone write it the other way around, but the MATLAB engineers apparently have it on their bookshelf. So unfortunately, we have to put a transpose in here when we calculate when we input the matrix into MATLAB. Okay. So 3, if P is positive definite, then x equals 0 is uniformly asymptotically stable. So basically, this equation is basically giving us our ellipse, right? P is just an ellipse in a two-dimensional problem. So basically, MATLAB is spitting out the ellipse for us. Okay. Like I said, It's not the only solution, but it turns out to be very convenient. And how would you pick other ellipses? Well, you could just pick different q's, right? So the value of q you use would change what ellipse you end up with for p. But any symmetric positive definite q will work. It will always produce a viable ellipse for you. So basically we get minimum eigenvalue of p times x squared is less than v, and v is less than maximum eigenvalue of p times the norm of x squared. So v is positive definite and decrescent. And we have v dot is less than or equal to negative maximum eigenvalue of q times the norm of x squared is negative definite. Okay, so from the theorem, this implies uniform asymptotic stability from the theorem. So I have a v that's positive definite decrescent, I have a v dot that's negative definite. That implies right away from the theorem that it's uniformly asymptotically stable from the Lyapunov theorem. Okay. That's kind of useless, isn't it? Because we started off knowing A had negative eigenvalues. So we already knew we had an exponentially stable system. So using the knowledge that we have an exponentially stable system, we were able to prove that we had an asymptotically stable system. That's a really useless result. So what I said so far isn't useful, but we'll see how it's useful later on. But the only thing it's useful for, it's useless in terms of proving stability. But what I've done is shown a way that we can calculate this ellipse. So calculating that ellipse will be useful for nonlinear systems. So theorem, A is negative definite if and only if given any positive definite symmetric Q, there exists symmetric positive definite P such that A transpose P plus PA equals negative Q. So I'll just make a note here, not useful in any way. So, let's see how we can actually make this useful. Linearization. x1 dot equals x2, x2 dot equals x2 squared, minus k1 x1 minus k2 x2 is my nonlinear system I'm going to analyze, where K1 and K2 are constant. So let's linearize this about x equals 0. So I get diF. So we'll call this F1, call this F2. So dif1 equals 0, dif1 dx2 equals 1. Di-F1, Di-F2, Di-X1 equals negative K1, and Di-F2, Di-X2 equals negative K2. So X dot equals Di-F Di-X evaluated at X equals 0 times X is my linearized system. So I have X dot equals 0, 1, negative K1, negative K2 times X. So if I'm going to calculate the eigenvalues, I have lambda times lambda plus K2 plus K1 equals 0. To calculate what my eigenvalues are, I get lambda squared plus lambda K2 plus K1 equals 0. So I end up with lambda equals negative K2 over 2 plus or minus square root of K1 squared minus 4K2 over 2. Hopefully you remember how to calculate eigenvalues and it doesn't look too strange. So the important part is that the real part of my eigenvalues is less than 0. I have minus K2 over 2. So in terms of the linear system, that's what I'm looking for, is that the real part is negative. As long as the real part is negative, then it's a stable system. So therefore, X equals 0 is locally exponentially stable. Locally because I linearized. So I basically designed, I've analyzed the stability of this, and I said, it's locally exponentially stable above this equilibrium point. So I was able to use kind of linear methods to analyze this linear system, this nonlinear system. But it might be important to know what local means. So if you have a linear system and you design a linear control, it's stable everywhere, so you don't need to worry about it. But if you have a nonlinear system and you design a linear control, you actually have to worry about where does that linear control work. Because if I wander too far away from that equilibrium point, that linear control can be unstable. So I do have to kind of worry about what I mean by local here. What do I mean by local? Where does it work? Because I want to make sure it works everywhere I need it to work. So just because it's locally exponentially stable doesn't mean it's going to work in real life. Because if I normally have disturbances that pull it out of that local region, then it can be an unstable control in practice. Right? So it may be really important what local means. So I'm going to choose Q to be the identity matrix. And in fact, I'm always going to choose Q to be the identity matrix. So like I said, choosing different Qs gives you different ellipses. So really any positive definite symmetric Q works, just results in a different ellipse. But there's some theory that says using Q as the identity matrix is actually the optimal solution. So in some ways it's kind of the best way to go. So I'm never going to use anything other than the identity matrix for Q. So it makes it really easy that way. So what I have to do once I solve that Q, or pick the Q I solve, A transpose P plus PA equals negative Q. So I have P equals, well I have A transpose Q in MATLAB. And MATLAB gives me 1.5, 0.5, 0.5, 1. So you can see that was the matrix I wrote it before in one of my examples. So now you can see I've shown you the trick for calculating these numbers. So I have eigenvalues of 0.69 and 1.8. So V equals X transpose PX is positive definite and decrescent for all X in region D. V dot equals negative X transpose QX is negative definite for all X in D. But what is D? It's a good question. So D equals R2 for the linear system. But we're not really talking about the linear system. We don't want to forget about those nonlinearities. What about the nonlinear system? Remember, the nonlinear system had the x squared in it, like that. So the procedure is, step 1, choose Q to be the identity matrix and solve for P. Based on the linearized system. Step 2 would be to use V equals X transpose PX and take V dot of nonlinear system. So let's see how this will work. So x1 dot equals x2, x2 dot equals x2 squared, minus k1 x1, minus k2 x2.